The afternoon of June 12, 1943, should have been routine for Lieutenant Akira Watanabe of the Imperial Japanese Army Air Force. Standing on the tarmac at Cagliari airfield in Sardinia, he watched Italian ground crews swarm around an American fighter that had landed moments earlier, its pilot bewildered, his compass broken, his fuel nearly spent. The aircraft was a Lockheed P-38 Lightning, twin-boomed, silver, and utterly intact. Within hours, Italian test pilot Colonnello Angelo Tondi would fly this prize to Guidonia airfield for evaluation. Within weeks, technical intelligence reports would circulate through Axis commands, and within months, Japanese engineers would be reading those reports with mounting confusion. The P-38G sat on the Italian airfield like a mechanical riddle. Its twin Allison engines, mirror images of each other, turned their propellers in opposite directions outward at the top of their arcs. Its counter-rotating configuration seemed simple enough on paper, a solution to torque problems that plagued conventional twins. But when Italian pilots test flew the aircraft with one engine shut down, they discovered something that contradicted everything Japanese aeronautical doctrine held true about twin-engine fighters. The Lightning flew on one engine not just adequately, but with a stability and control that seemed impossible. It climbed, it maneuvered, it returned to base. For Japanese observers reading these intelligence summaries in the summer of 1943, the revelation was less about American engineering prowess and more about the sudden, uncomfortable awareness that their own twin-engine fighters were fundamentally compromised machines. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. To understand why a P-38 flying on one engine seemed miraculous to Japanese engineers, one must first understand what happened when their own twin-engine fighters lost an engine. The Imperial Japanese Army fielded two primary twin-engine fighters by 1943, the Kawasaki Ki-45 Toryu, code-named Nick by the Allies, and variants of the Mitsubishi Ki-46 reconnaissance aircraft pressed into fighter service. Both aircraft shared a fatal characteristic. When one engine failed, particularly during takeoff or at low altitude, the asymmetric thrust created an immediate, violent yaw toward the dead engine. Japanese pilots called it the spin of death. The living engine, still producing full power, pushed its side of the aircraft forward, while drag from the failed engine pulled the opposite side back. Without immediate, aggressive counteraction, the aircraft would cartwheel into an unrecoverable spin. Japanese training manuals for the Ki-45 emphasized emergency procedures with grim specificity. If an engine failed below 3,000 feet, the pilot was instructed to reduce power on the operating engine immediately, feather the propeller on the dead engine if time permitted, and prepare for a forced landing. Attempting to climb on one engine was considered suicidal. The aircraft would stall before gaining enough altitude to be useful, the asymmetric thrust overwhelming the rudder's authority. Even experienced pilots with hundreds of hours in type spoke of the Ki-45's single-engine handling with barely concealed fear. The Nick was a capable aircraft with both engines running heavily armed, reasonably fast, effective against American bombers. With one engine out, it became a coffin. The fundamental problem lay in how Japanese engineers approached twin-engine design. The Ki-45's engines rotated in the same direction, both turning clockwise as viewed from the cockpit. This simplified production. Only one engine type needed to be manufactured, only one propeller configuration needed to be produced. But it meant that during normal operations, both engines generated torque in the same direction, requiring constant rudder pressure to maintain straight flight. More critically, it meant that during single-engine operations, the pilot faced an asymmetric thrust situation, compounded by propeller torque and P-factor, the aerodynamic phenomenon where the descending propeller blade on one side generates more thrust than the ascending blade on the other. The engineering philosophy stemmed from Japan's limited industrial capacity, manufacturing two different engine variants, one rotating left and the other right, would have doubled tooling requirements, complicated supply chains, and strained already scarce resources. Japanese designers made a calculated trade-off. They accepted poor single-engine characteristics in exchange for simplified production. They reasoned that twin-engine fighters would primarily operate in escort roles, far from Allied fighters. If mechanical failure occurred, pilots could attempt to reach friendly territory before the inevitable forced landing. What they had not anticipated was fighting against an opponent who had solved the problem they had accepted as unsolvable. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. The Lockheed P-38 Lightning represented a fundamentally different design philosophy. Chief Engineer Clarence Kelly Johnson and his team at Lockheed's Burbank facility had recognized the asymmetric thrust problem during the earliest design phases in 1937. Their solution was elegant in concept but demanding in execution. Make the engines rotate in opposite directions. The left engine turned counterclockwise, the right engine clockwise, both as viewed from behind. This counter-rotation meant that during normal flight, the torque from one engine cancelled the torque from the other. No constant rudder pressure was needed. The aircraft flew straight and true with neutral controls. But counter-rotation's real advantage emerged during single-engine operations. When one engine failed, the remaining engine's torque and P-factor were still present, still trying to yaw the aircraft. But because the engines were positioned symmetrically on either side of the centerline, and because they rotated in opposite directions, losing the left engine produced the same handling characteristics as losing the right engine. There was no critical engine, no situation where losing one particular engine was more dangerous than losing the other. More importantly, the counter-rotating configuration meant that the asymmetric thrust problem was geometrically balanced. The operating engine's propeller, regardless of which engine was running, created aerodynamic forces that could be countered with moderate rudder input. Achieving this required Lockheed to manufacture two different versions of the Allison V-1710 engine. The V-1710111 powered the left side, the V-1710113 the right. They were mirror images, their crankshafts turning in opposite directions. This doubled certain production complexities. Maintenance crews needed to stock parts for both engine variants. Assembly lines needed to ensure the correct engine went to the correct boom. But Kelly Johnson and his engineers believed the operational advantages outweighed the manufacturing burden. They were proven correct, though not in ways they initially anticipated. American pilots in the Pacific discovered the P-38's single-engine capability not through planned testing, but through combat necessity. The vast distances of Pacific warfare meant that mechanical failures often occurred hundreds of miles from the nearest friendly airfield, over open ocean patrolled by sharks and enemy submarines. Early P-38 pilots reported that when one engine failed, they experienced a moment of shock, the sudden asymmetric thrust, the immediate yaw, the nose swinging toward the dead engine. But then, following their training, they reduced power on the operating engine, trimmed the rudder, feathered the dead engine's propeller, and discovered something remarkable. The Lightning didn't want to spin. It didn't want to stall. It wanted to fly. With proper technique, a P-38 could maintain altitude on one engine at reduced weight. It could even climb slowly with careful power management. Pilots learned to limp home on single engines from distances that would have been impossible in any other twin-engine fighter. They learned to shut down a damaged engine mid-combat, feather the propeller, and continue fighting with reduced but still formidable performance. They learned to trust the aircraft's fundamental stability, the inherent balance built into its counter-rotating design. General George Kenney, commander of the 5th Air Force in the Southwest Pacific, understood the psychological dimension of this capability. In a 1944 interview, he explained his preference for the P-38 over single-engine fighters for long-range missions. A pilot in a P-51 Mustang, he noted, might be at peak efficiency at takeoff, but after 400 or 500 miles over open ocean, staring at nothing but grey water below, his effectiveness would degrade. He would arrive at the combat zone exhausted by anxiety, his morale at 50%. The P-38 pilot, by contrast, would arrive at 100% effectiveness. He knew that if one engine failed, the other could bring him home. That confidence translated into combat performance. Japanese intelligence officers compiling reports on captured American aircraft had access to detailed technical drawings of the P-38 by late 1943. Italian engineers had thoroughly documented the captured aircraft from Sardinia. German intelligence had analyzed P-38 seconds shot down over Europe. All these reports made their way to Tokyo, where they were translated, studied, and distributed to aircraft designers and military planners. The counter-rotating engines were clearly visible in the photographs. The technical advantages were explicitly stated in the reports, and yet the full implications seemed not to register. Part of the failure stemmed from the rigid separation between reconnaissance intelligence and operational doctrine in the Japanese military. Engineers could read about the P-38's single-engine performance, but that information didn't translate into actionable tactical guidance for pilots in the field. Combat reports from New Guinea and the Solomons mentioned American twin-engine fighters continuing to fight after sustaining damage that would have downed a Ki-45, but these reports were often dismissed as exaggeration or attributed to pilot error on the Japanese side. The possibility that American design philosophy had simply solved a problem Japanese engineers considered acceptable was not seriously entertained. The psychological dimension of the failure ran deeper. Japanese aircraft design in the early war years prioritized performance over survivability. The Zero fighter epitomized this philosophy. Light, agile, and lethal, but utterly without armor, self-sealing fuel tanks, or redundant systems. Pilots were expected to avoid being hit, not to survive being hit. Twin-engine fighters followed the same pattern. The Ki-45's heavy armament and reasonable speed came at the cost of single-engine controllability, but this seemed acceptable because competent pilots were expected to keep both engines running. The American philosophy, building in redundancy, accepting weight penalties to improve survivability, engineering systems to help average pilots survive situations that would kill exceptional pilots, was almost incomprehensible to designers trained in the doctrine of elite forces operating at the edge of performance. By the summer of 1944, Japanese pilots throughout the Pacific were encountering P-38 seconds with increasing frequency. They reported aircraft continuing to fight after clear, sustaining battle damage. Aircraft that should have been falling from the sky but instead climbed away toward friendly territory. Lieutenant Yoshio Okazaki, a Zero pilot stationed at Rabaul, filed a report in July 1944, describing an engagement where he had clearly seen strikes on a Lightning's right engine, observed smoke streaming from the cowling, and assumed the aircraft was finished. Instead, the P-38 pilot reduced power on the damaged engine, continued maneuvering with his wingman, and successfully fought off Okazaki's attack before disappearing into a cloud bank. Okazaki noted in his report that the American pilot's skill was admirable, but also that the aircraft itself seemed to possess capabilities that Japanese twin-engine fighters simply did not have. These combat observations began to accumulate in intelligence files, but by 1944, Japan faced more immediate crises than investigating the single-engine performance of enemy aircraft. The loss of experienced pilots, the shortage of fuel and raw materials, the relentless advance of American forces across the Pacific, these demanded attention. The mystery of how P-38 seconds flew so well on one engine remained just that, a mystery, noted but not understood, observed but not solved. Japanese engineers had the technical data, they had the photographs, they had the combat reports. What they lacked was the industrial capacity, the time, and perhaps the conceptual framework to redesign their twin-engine fighters around the principles the Americans had implemented from the beginning. The most detailed Japanese analysis of the P-38's design came not from combat intelligence but from a different source entirely. In early 1944, a young engineering officer named Lieutenant Takeshi Nakamura was assigned to Japan's Technical Research Institute in Tokyo. His task was to review all available intelligence on American aircraft and prepare recommendations for Japanese designers. Nakamura was 26 years old, educated at Tokyo Imperial University, fluent in English, and possessed of a questioning mind that hadn't yet been beaten down by military hierarchy. When he read the reports on the captured P-38 from Italy, He immediately recognized the significance of the counter-rotating engines. Nakamura prepared a detailed technical memorandum. He explained the aerodynamic principles of asymmetric thrust. He diagrammed how counter-rotation eliminated the critical engine problem. He calculated the handling advantages during single-engine operations. He noted that Lockheed had accepted the manufacturing complexity of two engine variants in exchange for operational advantages that Japanese pilots desperately needed. His conclusion was unambiguous. Japanese twin-engine fighter development should prioritize counter-rotating engines in all future designs, even at the cost of production efficiency. The memo was forwarded up the chain of command. It was read, acknowledged, and filed. No design changes were implemented. No new counter-rotating fighters were developed. The industrial reality of Japan in 1944 made such changes impossible even if they had been deemed desirable. The captured P-38 Italy never reached Japanese hands for direct examination. Italian collapse in September 1943 meant that the aircraft either was destroyed or fell into Allied hands before it could be shipped to Japan. But the intelligence it generated, the photographs and technical drawings and test pilot reports, circulated widely enough that informed Japanese engineers understood what they were facing. The Americans had built a twin-engine fighter that treated engine failure as an inconvenience rather than a catastrophe. Japanese engineers had built twin-engine fighters that killed their own pilots when engines failed at the worst possible moment. The gap represented not just different engineering solutions but fundamentally different philosophies about what role aircraft should play and what risks pilots should be asked to accept. The consequences of this engineering divergence played out across thousands of square miles of Pacific sky. While Japanese pilots faced engine failures with dread, American P-38 pilots developed a confidence that bordered on casual. Combat mission reports from 1944 and 1945 are filled with matter-of-fact entries. Lost right engine to anti-aircraft fire over Rabaul at 14:30. Feathered prop, maintained formation, completed mission, returned to base on single engine. These entries appear with such frequency that they cease to be remarkable. For the Americans, single-engine operations became routine. For the Japanese, they remained mysterious and impossible. The asymmetry extended beyond simple mechanical capability. It shaped tactical doctrine, mission planning, and pilot psychology. American commanders regularly assigned P-38 seconds to ultra-long-range missions, knowing that engine redundancy provided a margin of safety. The assassination of Admiral Isoroku Yamamoto on April 18, 1943, exemplified this confidence. The mission required P-38Gs to fly over 400 miles from Guadalcanal to Bougainville, mostly over open ocean, engage Japanese fighters and bombers, and return. The entire operation depended on the assumption that if a Lightning suffered engine problems en route, it could continue the mission or abort and return on one engine. No Japanese twin-engine fighter could have attempted such a mission with comparable confidence. Individual pilot accounts reveal the psychological dimension most clearly. Second Lieutenant Rex Barber, one of the pilots who shot down Yamamoto's bomber, later described the feeling of flying long over water missions in a P-38. "You knew that if you had an engine problem, you still had options," he recalled in a 1976 interview. The other guy was still running. You could work the problem, make decisions, maybe make it home. In a single-engine fighter, you had one option: ditch and hope the rescue boat found you before the sharks did. This confidence allowed American pilots to focus on the mission rather than worry about mechanical reliability. Japanese pilots in twin-engine fighters had no such luxury. The engineering reality created a feedback loop that amplified initial differences. American pilots, confident in their aircraft's single-engine capability, pushed P-38 seconds harder, accepting risks that Japanese pilots in key 45 seconds would never consider. This aggressive employment generated more combat successes, which justified further production, which allowed for continued refinement. By 1945, the P-38 Liters incorporated years of evolutionary improvements, including uprated engines producing 1,475 horsepower each, improved supercharging for high-altitude performance, and increased fuel capacity for even longer range. The single-engine capability that had been designed into the original remained, now enhanced by more powerful engines that made single-engine flight even more reliable. Japanese twin-engine fighter development, by contrast, stagnated. The Ki-45 received minor upgrades, better armament for anti-bomber work, primitive night fighter equipment, improved engines, but the fundamental single-engine handling problem was never addressed. Japanese designers understood the issue. They had access to the technical solution, but implementing counter-rotating engines would have required retooling production lines, developing new engine variants, retraining maintenance crews, and accepting temporary reductions in output while the changes were implemented. In 1944 and 1945, as Japan's strategic position collapsed, such changes were impossible. The industrial base that might have supported redesign was being bombed into rubble. The experienced engineers who could have led the effort were being drafted or reassigned to more desperate priorities. The time and resources that counter-rotation required simply did not exist. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The human cost of this engineering failure is difficult to quantify but undeniable. Japanese aircrew losses in twin-engine fighters included an unknown but significant number of pilots who died not in combat but in takeoff or landing accidents when one engine failed at the worst possible moment. Training command records from 1944 show recurring incidents. A Ki-45 attempting takeoff with one engine misfiring, the pilot pushing throttles forward trying to maintain airspeed, the asymmetric thrust overcoming rudder authority, the aircraft cartwheeling into the ground off the end of the runway. These deaths didn't generate combat loss reports. They were classified as training accidents, operational losses, mechanical failures, but they were as surely casualties of design philosophy as any pilot shot down in aerial combat. By contrast, P-38 training accidents related to single-engine operations were remarkably rare. The aircraft's counter-rotating configuration, combined with proper training on single-engine procedures, meant that engine failures during training rarely resulted in loss of aircraft or crew. This difference in training safety meant that American pilots could practice single-engine operations extensively, building the muscle memory and confidence that would save lives in combat. Japanese pilots, facing an aircraft that might kill them if they practiced single-engine procedures too aggressively, received minimal training in an area where they desperately needed experience. The final irony came in the war's last months. As American forces closed on the Japanese home islands, the requirement for long-range bombing escorts disappeared. The P-51 Mustang, lighter, faster, cheaper to produce, and with comparable range, began replacing P-38 seconds in many roles. The Lightning's twin-engine redundancy, so valuable over Pacific expanses, became less critical when missions originated from bases in the Marianas or from captured fields in the Philippines. By August 1945, many P-38 units had converted to P-51 seconds. The aircraft that had dominated Pacific skies through 1943 and 1944 was being phased out, not because it was inadequate, but because simpler designs could now accomplish the mission. But during its operational peak, the P-38's counter-rotating engines and single-engine capability had shaped the Pacific Air War in ways both obvious and subtle. The obvious impacts showed in mission capability, ultra-long-range strikes that Japanese forces couldn't counter, bomber escort that allowed American heavy aircraft to operate with relative impunity, reconnaissance missions that penetrated deep into Japanese-held territory and returned safely. The subtle impacts showed in pilot confidence, mission planning flexibility, and the psychological advantage of knowing that mechanical failure didn't necessarily mean death. These advantages, cumulative and interlocking, contributed to air superiority that by 1944 had become total dominance. The captured P-38 Sardinia represents a perfect symbol of this divergence. Italian engineers examined it, flew it, documented it, and sent their findings to allies, including Japan. The technical information was accurate and complete, the implications were clear, and yet the information couldn't be translated into action, not because Japanese engineers lacked understanding, but because the industrial and strategic context of 1943 and 1944 made fundamental redesign impossible. The counter-rotating engines that gave the P-38 its single-engine capability required a manufacturing base, a supply chain, and a strategic situation that Japan no longer possessed. By the time Japanese engineers fully understood what the Americans had achieved, it was too late to match it. Lieutenant Nakamura's memo, buried in Tokyo archives, demonstrated that understanding existed. The American Lightning possesses handling characteristics during single-engine operations that our Ki-45 cannot match, he wrote in his February 1944 report. This advantage derives from counter-rotating engines, a feature that our current production capacity cannot easily implement, but which should be prioritized in all future twin-engine designs. The memo included detailed calculations of torque effects, diagrams of propeller rotation, and recommendations for emergency modifications that might improve Ki-45 single-engine handling without requiring new engines. None of these recommendations were implemented. The memo sat in a file cabinet in Tokyo as American P-38 seconds ranged across the Pacific, their counter-rotating engines turning in perfect opposition, their pilots confident that one engine could bring them home. The engineering lessons of the P-38's counter-rotating configuration extended far beyond World War II. Post-war American aircraft design incorporated the principle broadly. The Lockheed P-2V Neptune maritime patrol aircraft, the Douglas A-26 Invader attack bomber, and numerous civilian twin-engine designs adopted counter-rotation as standard practice. The principle became so established that by the 1950s, it was simply assumed that any serious twin-engine design would feature engines rotating in opposite directions. The manufacturing complexity that had seemed daunting in 1937 had become routine in the post-war aviation industry. Japanese post-war aircraft development, ironically, benefited from these lessons. The Japan Self-Defense Air Force, established in the 1950s, operated American-designed aircraft, including some surplus P-38 seconds. Japanese engineers who had puzzled over the Lightning's capabilities during the war now maintained and flew them. The mystery that had seemed so profound in 1943 became simple engineering orthodoxy. Counter-rotating engines were not a breakthrough innovation but standard practice, so obvious that questioning them seemed strange. The gap between 1943 and 1955 was only 12 years, but the transformation in understanding was total. Yet, during the critical years of the Pacific War, that gap in understanding shaped combat outcomes in ways both dramatic and subtle. American pilots flew with confidence born of redundancy. Japanese pilots flew with anxiety born of mechanical fragility. The difference wasn't just engineering, it was psychological, tactical, operational, and it stemmed ultimately from design decisions made in a Burbank office in 1937. Decisions that prioritized operational capability over production, simplicity, decisions that valued pilot survival over marginal performance improvements, decisions that looked at the problem of asymmetric thrust and refused to accept it as unavoidable. The P-38 Lightning flew its last combat missions in August 1945. Production ended shortly thereafter. The aircraft that had seemed so revolutionary in 1942 was obsolete by 1946, superseded by jets, rendered unnecessary by peace. But its counter-rotating engines had solved a problem that Japanese engineers never adequately addressed. In the vast sky over the Pacific, where distances were measured in hours and fuel consumption in gallons per minute, where engine failure might mean death by drowning or shark attack or simple exposure, the ability to fly home on one engine wasn't a minor feature. It was survival. It was the difference between mourning parents receiving a telegram and a pilot walking off a flight line after an emergency landing. It was engineering translated into life and death, design philosophy manifested in aluminum and steel and determination. The Japanese never built a counter-rotating twin-engine fighter during World War II. The Ki-45 served until the war's end, its single-engine handling problems never resolved. Pilots learned to fear engine failures, to treat takeoffs and landings with extra caution, to accept that one engine failure at the wrong moment meant certain death. They adapted to the aircraft they had, developed procedures to minimize risk, and died in numbers that might have been reduced if Japanese designers had made different choices in 1937. But those choices weren't made, and by the time the problem was fully understood, solving it was impossible. The Lightning's legacy, therefore, is not just the aircraft itself, but the philosophy it embodied. Counter-rotation, redundancy, engineering designed to help average pilots survive extraordinary situations. These principles shaped American military aviation for decades. They represented a fundamentally optimistic view of technology's role, not to create perfect machines for perfect pilots, but to create forgiving machines that helped imperfect humans survive imperfect situations. The P-38's counter-rotating engines were just one manifestation of this philosophy. But in the skies over the Pacific, where Japanese pilots struggled with asymmetric thrust, and American pilots flew confidently on one engine, that manifestation made the difference between victory and defeat, between survival and death, between understanding the problem and solving it. The captured aircraft in Sardinia, examined by Italian engineers in June 1943, represented all of this. The solution to a problem, the embodiment of a philosophy, the physical manifestation of industrial capacity and design confidence. Japanese engineers read the reports, saw the photographs, understood the principles. But understanding wasn't enough. The gap between knowledge and implementation, between recognizing a solution and possessing the resources to adopt it, proved unbridgeable. The Lightning flew on one engine because American engineers in 1937 decided it should. Japanese twin-engine fighters couldn't because Japanese engineers in 1937 decided that other priorities mattered more. By 1943, when the consequences were clear, the decisions couldn't be reversed. In the final accounting, the mystery of the P-38's single-engine capability wasn't mysterious at all. It was engineering. It was design philosophy. It was the cumulative result of 1,000 decisions about what mattered most in aircraft construction. The Japanese captured a P-38 Lightning and couldn't understand how it flew on one engine, not because the principles were incomprehensible, but because implementing those principles required resources, time, and priorities that Japan in 1943 no longer possessed. The aircraft sat in Italian hangars, its secrets exposed and documented, its advantages clear and quantifiable, but secrets that cannot be acted upon remain merely theoretical. The counter-rotating engines turned in perfect opposition, one clockwise, one counterclockwise, cancelling each other's torque, providing redundancy, offering confidence, and Japanese engineers, reading the reports in Tokyo, understood perfectly what they were seeing. They simply couldn't build it themselves. Up next, you've got two more standout stories right on your screen. If this one hits the mark, you won't want to pass these up. Just click and check them out. And don't forget to like, subscribe, and turn on the notification bell so you don't miss any upload from us.